How's it going, everybody? Here's another good day of dynamics. Here's our problem. It says the motion of a 6,500-pound boat is arrested using a bumper which provides a resistance as shown on the graph. All right, that's that right there. Determine the maximum distance the boat dents the bumper if its approaching speed is 3 feet per second. So they say you got 3 feet per second right there. So let's pick it apart and see what we can do. So we got a mass. Well, it's not really a mass. We have a force, but it's used as a mass. Whenever they give you the weight of something, you're basically using it as a mass. So they gave us a mass. All right. So the moment I see mass, I know I'm going to be doing kinetics, which is going to be free body diagrams. It's going to be work energy, or it's going to be impulse momentum. So it's got to be one of those three. It's got to have one of those three others. All right, they tell us the bumper has a resistance as shown in this graph right here. So this graph represents the force that the spring puts, or excuse me, not the spring, the tires, they look like tires, the tires put on the boat as you go deeper. So mind you, as you go deeper into the tire, as you push further into the tire, the force of the tires push back harder. So if you think about it like a rubber ball, you can't squeeze a rubber ball into nothingness. You squeeze on it a little bit and it starts to give in the beginning, but the harder you squeeze, the more it gives back. The more you squeeze it, the more you push it in, the stronger it pushes back. Okay, so that's what this graph represents. All right, cool. So they gave us that data. They say determine the maximum distance, so that's what we want. Maximum distance the boat dents the bumper. All right, cool. Actually need to make that smaller. So determine the maximum distance the boat dents the bumper. All right, cool. So basically they want S. They want S at the point where it stops. So think about it like that. So basically they're saying, what is S at velocity equals 0? So think about it. It's coming in with 3 feet per second. It's going to hit the tires, and then it's going to push in the tires. And when it finishes pushing in the tires, the boat's going to have stopped. So basically, when the boat stopped, how far did it go in? So what is S when the velocity is 0? All right, so we're going to be doing work energy. How do I know we're going to be doing work energy? So remember this. Free body diagrams, it's one instance. One instance. It could be one place, it could be one time. The whole idea is that they're going to give you a specific point in time or space, and they're going to say, find me acceleration, force, or some kinematic variable like velocity or something like that if you're going in like radial transverse or normal tangential coordinates. Work energy is going to be two places, so two positions. Okay? How do I know we're talking two positions? The moment I see positional data and like mass data, my thought pattern's automatically always going to go to work energy. Okay, so the fact that I'm going to start at basically S equals 0 and then go to some value of S, I don't know it, but I have to start from S equals 0 to S2, which is going to be some value of S. I have two positions. That's going to make me think work energy. Why would it not be impulse momentum? Impulse momentum is 2 times. They don't say at what time does the boat finish denting the bumper. If they said at what time the boat finishes denting the bumper, we'd be doing the impulse momentum problem. Okay, so because we want to find the position of this situation based on like a starting and stopping, we're going to be doing work energy. So bam, 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 bam. So we're going to be doing work energy. All right, cool. This right here is very important, so I'm going to highlight it. I just kind of denoted it, but that's going to be a piece of information that we need. So let's get started with our work energy method. All right, so the equation for work energy is as such. Some people learn it a little bit different. Some people learn it, in steps. I never have agreed with that. I'm just going to give you the end product of when you finish learning it. I say the initial kinetic energy plus the initial potential energy plus the work done from 1 to 2 equals the final kinetic energy plus the final potential energy. All right, cool. So for those of you who haven't gotten the potential energy, don't worry about it. Just know that in this problem there actually isn't any potential energy. This is what I say. This is the thermodynamic rendition of the work energy equation, which is where it comes from in the first place. I think this is the most pure form of the work energy equation. I don't like the way they presented the dynamics, so I'm presenting it my way. So let's do some cutting and pasting. There is no potential energy. Potential energy comes from springs. Okay, the energy stored in springs, and the energy stored. Well, I shouldn't say stored. The work done by gravity. So all the work that would be done by a spring, all of the work that will be done by gravity, all of the energy stored in a spring, all of the energy stored in a potential height, in a height difference. All of that stuff gets locked into potential energy. All right. We don't have to worry about gravity because the boat's not falling and there are no springs. Yes, some people will say, but the tires are springs. Yes, but that's not the case that we're not considering that right now. That's not how we're approaching this type of problem. All right, and it'll make more sense as you practice these problems. All right, so we know that the potential energy in the beginning and end do not exist because there are no springs or gravity to be considered. The kinetic energy is going to go to zero. Why is the kinetic energy going to go to zero? Because I said, what is S at V equals zero? Well, if you think about it, in the beginning, on the left side of the equation, S equals zero, right? On the right side of the equation, S equals some value. So S1 and S2. But the velocity, the first velocity is 3. The second velocity has to be 0. Well, kinetic energy is given as 1/2 mv squared. If the velocity is 0, then I can say that the kinetic energy at the final is going to be 0. So what I'm left with is this. Kinetic energy 1 plus the work from 1 to 2 equals 0. All right, so a lot of people go, well, one of these guys has to be negative. Well, kinetic energy can never be negative. I'm going to say that right now. Kinetic energy can never be negative. Because inherently, if you look at the equation for kinetic energy, it's 1/2 mv squared. Actually, you know what? I'll put it in a box. Because that's important, that equation right there. It's important. So, no, I don't like that. I'll just underline it. Yeah, just like that. All right, so kinetic energy can never be negative, but work can be negative. So when can work be negative? In this case, work is negative. So I'm gonna just kind of say that work is negative. So work is negative whenever it drains energy from the system, which only really happens in two situations. Work is negative when it comes from friction. Okay, think about it. Friction only ever slows things down. You've never seen friction speed something up. You've never seen friction give energy to anything. Friction is always negative work. And then whenever something is slowing something down, that is going to be considered negative work. In our case, the boat is moving at 3 feet per second, and it's going to slow down to 0 feet per second. That energy is being drained out of the boat via the tires. The tires are draining the boat of its energy. So it comes from friction or stoppers. I'll just put quote unquote stoppers because technically that's what we're working with, some sort of stopper. So because of that, we know the work is actually negative. So what I'm going to do is I'm going to rewrite this term. Instead of putting plus, I know work is negative, so I'll put a minus right there. Okay. So with that being said, I can rewrite our thing. So I can say the work from 1 to 2, if you move it over to the right side, equals the kinetic energy at 1. Bam. This is the simplified rendition of the work energy equation. This is how you apply work energy to a problem. You start with the big form of the work energy equation, and then you chop until you're left with the things that you can work with. Well, work's definition is the integral of force dot ds. All right. A lot of people see that as force times distance. So I'm gonna say it like this. Work is force times distance when it's not a function. When force is constant, you use force times distance. When force is given as a function, like we have, you're going to use the integral, okay? So I'm not going to have a lot of force.ds integral problems, but you definitely need one every once in a while, okay? So I'm going to use that. Just remember that whenever force is a function, you use the integral. Whenever force is constant, you just use F times S. So that's equal to kinetic energy. Kinetic energy is 1/2 mv squared. Cool. I'll put v1 squared. All right, great. So let's kind of rewrite that even still. Well, the force is 3,000. 3 times 10 to the third is 3,000. I'm just going to put 3k because I'm lazy. I can pull that out because it's a constant, and then I have s cubed, and that's got to be ds. Okay. It's not dot ds because the dot product, I'll put it right here. The dot product basically gives a sense of direction. Okay. So the F dot ds means the force in the direction of S. If you take a look at our situation here, the force is always the velocity, and hence the force is moving in the same direction as S, and therefore the dot product nullifies into 1, into the value 1. And so whenever you have F dot ds and the force and the distance that the object is moving are in the same direction, you just put Fs. You just put F times S, and it works out. So that's why I could put S cubed times ds instead of dot ds. Okay. The dot just means you have to use a cosine if they're not at the same angle, and that'll make more sense as we do more problems. Okay. So we have that on the left side has to equal 1/2, and I put my mv squared on the right side. All right, cool. And from here, if I take my integral is going to give me 3k at first, and then my integral gives me s to the 4th power, and I divide it by 4. It's got to be equal to 1/2 mv1 squared. Okay. And then from here, I can basically literally solve this equation for s. So bring it down one more time. I don't really like the way this is moving. Let me just keep moving it to the right. So move everything over. I'm going to have s equals, I take the 4th root, and it's got to be mass v1 squared. And then I have to multiply it by 4, but 4 over 2 is going to be times 2. So I can put times 2 right here, divided by 3,000. And that's going to be some number. I know these values. Mass is going to be, they told us the weight of the object was 6,500 pounds. Do not put 6,500. It's going to happen. I do it all the time. It's 6,500 divided by 32.2 because weight in American units is a force and not a mass. So you have to divide by acceleration, 32.2. V1 is 3. They told us it was coming in at 3 feet per second. All right, cool. So when you plug in all your numbers, you plug in chug, you're going to get 1.05, and that's going to be feet. And that's our answer, okay? So, simple enough. The trick to doing work energy problems is in understanding how to set them up, how to pull information out, and basically, once you're able to set up this equation and then pull information out to the point where it becomes applied to what the problem states, everything from there is just plug and chug. All right, and it'll make more sense as you continue to watch problems be done. And I have a method that I like to use that makes life really, really easy. So hopefully this made some sense. I think I've never met students who did not intuitively understand energy and how it flows, just because at this point in your lives you understand that when you push something it moves, and then friction pulls the energy out of it as it moves. So energy is a very intuitive concept, and because of that, typically work energy problems are easier in the dynamic spectrum. So if you like this video, please like and subscribe. I got a goal. I'm trying to make sure I get up as many mechanical and electrical engineering videos as possible. And your support will be greatly appreciated. So with all that said, thank you, and I hope this helped.